So I will start this presentation on BSR-derived heat flow versus marine probe heat flow. So we go back to the sea and to some methods for acquisition of marine heat flow. Florian already explained in detail the marine heat flow probe method and some of the nice results they got with it. So here I will focus on this BSR-derived heat flow, and then in the end show some comparison with marine probe heat flow data. I put this picture here from a study that I did with my colleagues from Ghent in the late 90s, early 2000s in Lake Baikal, because it shows very nice the possibilities. You can see here on the left, you have a map of a heat flow derived from a BSR. So you can see you have a very nice regional information on the variability of heat flow in this complex tectonic area. On the right side, you can see, however, that it's not always so easy to interpret and that there are sometimes some discrepancies with probe measured heat flow. That is not always negative. That can always also help us to learn something more about the systems that are acting below. So, but let's go step by step. Okay, so what is a BSR? For people who are not never worked on seismic profiles, a BSR is an acronym for bottom simulating reflector. So it's a special reflector that can be observed sometimes on seismic reflection data. As you can see here on the example, this is again an example from Lake Baikal. And you can see that around 320 meters below the lake floor, you see that there is a relatively strong reflector here that mimics more or less the seafloor. So when the seafloor goes up, it also goes up. And more striking is that it cross-cuts the layering. You can see it especially here when you have, like in this anticline, you have some layers that are not subhorizontal anymore. So this specific reflection is what we call the BSR, or the bottom simulating reflector. So where does it come from? So it's the result of an impedance contrast between gas hydrates on top of free gas. So if you see here on the right image, you see that we have this layer here in the sediments, and then there is a part where we have some gas hydrates and just underneath free gas. This gives a very strong impedance in the seismic reflection data. So what are these gas hydrates? So again, these gas hydrates are ice-like structure that contains a lot of gas, especially methane. So the gas is compressed in high quantities, and when you take it to pressures of atmosphere, this gas will escape, and you can see that you can light it on fire. So that's why they call it the burning ice. So this specific gas hydrate is what gives this BSR, so this bottom simulating reflector. So here on the right, I put the phase diagram of a mixture of methane gas and water. And you can see that for temperatures in the sea, so in the water column and in the sediments, we can be or in methane gas and water, or in an area where the gas will be the gas and the water will be transformed in hydrates, in gas hydrates. So we don't, there may be some exceptions. In most cases, we don't come in any area of water ice. So again, on this picture, what you can also see is that for shallow water depths, we will never come in an area where we can methane hydrates. So in order to have the methane hydrates, we need to go at water depths of around 380, depending on different conditions. So once we are like 300, 500 meters in water depth, we can start to have gas hydrates. But then they will also stop to exist because the temperature in the sediments increases, and at some point we go again to the methane gas and the water, so without hydrates. So this is the point where we get this contrast between hydrates on top and the gas below. So this picture is from a cruise that we did in 2003 on the Amazon Delta, deep sea Delta. So, well, to explain the last that I told you a bit more in detail, this is a focus, so it's the same diagram, but the focus on only the deep sea. So this is specifically for Lake Baikal, so it's for fresh water. It's a bit specific, but it shows exactly the same dynamics of where is stability and where not. So just to show that in principle, according to the phase boundary diagram, the hydrates can be stable in the water from a certain depth up to where we cross, as I told before, the geotherm that increases too much. In the water, unfortunately, hydrates are rarely formed because of it cannot fix in the water. But in the sediments, it can form in this part of the upper part of the sediment, so not anymore below. There are a lot of conditions that need to be filled, also some flux and saturation conditions. So it's not because it's in the stability that there will be hydrates. So again, here to show that in shallow water depth, we will not have a BSR, or very close to the surface. And when we go deeper, you see the BSR will be deeper in the sediments. Okay, where do we find these BSRs? You can see on this this map from a review publication of Xi last year, that they are quite widespread, mostly on the continental margins and marginal seas, but also, as I told you already, in Lake Baikal. So why are they limited on the margins? Well, you need enough organic matter to produce enough methane gas also. So that's why probably they are mostly limited to margins and not to the very deep sea, offshore deep parts. Again, the morphologies of the BSR is highly variable and will depend on the geological environment. Here is this picture again from the same publication that shows that the BSR is so normally mimicking the seafloor, so it's very continuously, but in some places it can be very local, and it can also form like this kind of up-domed morphologies, so it's not mimicking anymore the seafloor. So to show here the same thing on this geological dependence, you see that here is an example from the lower Congo Basin. You can see that the BSR here in blue, the patches, are found in the basins between some salt diapirs. So it's very depending on the environment. Another thing that makes it a bit complex for us, if we want to derive the heat flow, is the fact that sometimes we observe multiple BSRs, so double or even up to 4 BSRs have been observed at the same location. So this is an example from the Danube sea fan from the gas project, and you can see here there is something called BSR-1, which is the BSR according to the actual conditions, but there is another BSR here that has been observed. And according to the studies that have been done there, it is like a paleo BSR. So it's reflecting some conditions, in situ conditions, from previous times. In this case, from the last glacial maximum. Here in this area, it is the diffusion of the salt. So it's a change of the salinity in the pore waters that have created a shift of the BSR from one place to another. But there is a delay of the hydrates dissociation in this area, so the second BSR stays in place. Okay, come to the main thing. That's how we get the heat flow from the BSR. So the BSR gives us an indirect sediment temperature estimate. So as you see, in an area where we have a BSR, if we have information on the temperature of the water and especially of the bottom water. Then by using this methane hydrate stability curve, so from the phase diagrams, we have to assume, of course, a gas composition, salinity, and some other characteristics. But in that case, if we have it, the crossing of this with the depth of the BSR will give us a temperature of the BSR in the subsurface. It means we have the bottom water temperature and we have this BSR temperature, which can give us this linear gradient between the 2 points. So to go to the heat flow, we have to obtain, of course, also the thermal conductivity in this area between the seafloor and the BSR. The first one to have been proposed to use this as a heat flow estimate is the article by Yamano in 1982. So you see the equation that has been used. So it's an easy principle, but it's not so easy to quantify the different parameters that we need in order to get this estimate. So this is what I will try to show in the next slides. So here is a simplified version of this equation. And you can see these are different parameters that we need to know in order to define these main parameters. And all of them can introduce an error which can be considerable. So it's important to look at each of them in detail when you're doing the heat flow estimates from BSR. So I will go now quickly through these different parameters and show a little bit why they are so important and on this heat flow estimate. So first of all, the phase diagram of the hydrates. This is based on experiments in the laboratory. So in general, they are made on limited PT conditions. So not ranging all the PT conditions that we have in the offshore. And so you can see here, for example, where postdoc Eloise did an exercise, and so here you have the data, and if you extrapolate this data to deeper depth, you can see that you can get quite a difference in the phase diagrams used. And so this can introduce a big error and an uncertainty on the estimate. The phase diagram is also a function of especially salinity and gas composition. If you see this map of the salinity of the seafloor, this is from WOA 2018 database. Of course, in many parts of the ocean, it's quite stable. But if you go in the areas of interest, the continental margins, you see that you can have a strong variability of salinity. So it's very important to consider, and also to consider the difference that maybe exists in the sub-seafloor, not only the salinity from the seafloor. So I show here an example of the effect it can have on the phase diagram. This is again and you see here that the reference one, which is from methane and seawater, so like around 34.8 per milli. But if you look in freshwater, like in Lake Baikal, you will have already a shift here, you see, which is almost 2 degrees at this depth of this phase diagram. So then if you change the composition of the gas and you don't only consider methane, but that there is also ethane in your gas system in the sediment, you see that you can have a very big shift. So any additions of higher carbon gases can strongly shift this phase diagram limits. So very important to consider. Another thing for the phase diagram is that in most cases, we will assume for the part that concerns us, so from the sea floor up to the BSR depth, we will assume lithostatic pressures. But this is not always the case. So sometimes there are overpressures. So here is an example from this article of Dungan and Sheehan. And just to show that it can be considerable, and it has in some environments has to be considered in order to have good estimates of the temperature at the BSR. So the fourth parameter is a seafloor temperature. Again, this map, another map here with now the seafloor temperature. Globally, you see the high variability that exists. So if you only have seismic data and you don't have any information from CTD or from other sources about the temperature of at the bottom of the sea, it's very difficult to define this parameter very accurately. And it will influence a lot, as shown here by this example from some temperatures of different seas, and how you get in an fictive example different heat flows by the same BSR depth. So the last that I want to mention is the depth of the BSR. So the BSR is coming from an interpretation of a seismic data. These seismic data are normally in two-way travel time in origin. So they have to be converted in depth in order to have the exact depth of the BSR below the seafloor. And so for this conversion, we need some velocity of the seawater and the sediment, seismic wave velocities. This is not always the case, especially for older data. For more recent data, we have very often better estimates on these seismic wave velocities. The last one of the parameters that's important is the thermal conductivity of the sediments. This also can be highly variable in the continental margins. I showed this example from a publication of Strane and O'Regan, so showing that sometimes conductivities can be quite constant up to depths of BSR, but in other areas you get a clear increase, sometimes linear, sometimes exponential. So this is a simple interpolation map that we made once from the global heat flow database at the time, showing the variability of the shallow, the conductivity of the shallow sediments. So considering all these uncertainties of these different parameters, what is the global error that we can estimate on a heat flow derived from the BSR? So this is an exercise taken from a review paper of Willinger. We have done the same. We come more or less to the same conclusions. And you can see that on the gradient, we can estimate an uncertainty of 5 to 35%, 2 to 20 on the thermal conductivity. So a combined one of 10 to 55 for the heat flow derived from BSR. So if we compare this to the marine probe data, we see that there is a higher uncertainty in general on a BSR-derived data than on marine data. But in some conditions, we come very close, or we can come to almost the same accuracy. Just to remind you that the probe data is only done in the very shallow part of the sediments, in general, only 5 to 10 meters. 3 to 10 meters, let's say. Well, the BSR will give information over a gradient that's between the seafloor and the BSR depth, so over much larger depth distances. So is this confirmed by data, by measurements in situ? So there have been some boreholes, IODP, ODP boreholes made in places where BSRs have been observed. In the beginning, there had been some publications that mentioned anomalous cold BSR. So this publication here from 1907 from Ruppel. So you can see on this image that normally the gradient here, and this is the hydro stability, will cross somewhere at 550, while the BSR here is only at 450, so has colder temperature than what was expected. But recently, there is a paper that has reconsidered some of the different parameters, and that comes to a base of the gas hydro stability zone that is correctly estimated at the base of the BSR here. Just another example from a recent publication from results of from the IODP in the Cascadia accretion area wedge, where there has been a 4-year observatory using the cork system, so which prevents any strong circulations due to in the borehole, so to have much better temperature measurements. And so they also, after this 4 years observation, comparison with the BSR, found a very good fit between the depth, between the temperature estimated from the hydrate stability diagram and the one measured in the borehole. So if we compare now the BSR-derived heat flow with marine probe heat flow, what do we see? There have been some publications where we see a strong discrepancy between both of them. I give 2 examples here. One was on the read from the Macron accretionary wedge from Cole and colleagues. And you can see that here in this case, the heat flow probe data is quite lower, up to 50% than the BSR-derived heat flow. On the other hand, another example from the South China Sea, where it's the opposite, and the probe data is much higher, more than 50%, which is the maximum uncertainty that we estimated, than the BSR heat flow. They raised different possibilities to explain this in both publications. So for the Macron, it was more the velocity porosity model that was poorly constrained, and the sedimentation model that had to be developed more. Here in the South China Sea, they questioned the theoretical assumption of the BSR. However, there are a lot of studies where we have a very good overall correlation. So here on the left side, an example from the Costa Rican margin, from a publication of Harris and colleagues in 2010, where you can see, especially here in the middle panel here, where the dots are the heat flow probe data and the blue line is the heat flow derived from the BSR, and you see a very nice correlation. So the only places where you have a disparity is where the measurements are close to seep sites. So the red triangles here are seep sites. Another example is from a study of me and my colleagues in Artibonite Basin offshore Haiti. So here we didn't have a lot of heat probe data, but you see that our heat flow data fits very well with the estimates of the BSR that we observed. And the BSR in this case gives a very useful tool to extrapolate. You see that we had in the basin only 3 measurements, but it allows us to extrapolate the heat flow in a larger area of the basin than only on these 3 locations. So another example I will show is from a more recent study that we did in the Amazon deep sea fan, in order to show that the discrepancy between the BSR derived and the marine probe heat flow can sometimes give useful information. So these are 2 examples from a 3D seismic cube, where a BSR has been observed in a compressional area on the Amazon deep sea fan. So where you have quite a lot of seep and mid-volcano structures in an anticlinal, we have some anticlinal sediment structures. And you see, if we compare the BSR-derived heat flow with the probe heat flow data, which are here in red dots, you can see that it fits quite well if we are out of the seep and the mid-volcano area. But once we are in the seep, here and here in this broader area, we get values that are much higher. So this is interesting, and we use this information in order to see what could be the source of the escaping methane and fluids. And if we use these increased heat flow values and also a little bit the nonlinearity of the profile in a very simple 1D steady state heat fluid model, this gives a very nice constraint that the depth of the source of these fluids should be 150 meters, which more or less correspond to the depth of the normal BSR. So it looks like the BSR, well, one interpretation could be that the BSR has been dissociating by warm fluids, and that then this warm fluid at certain moments escape to the seafloor and give these nonlinear profiles. Well, to resume, the take-home message is that both BSR-derived heat flow and marine probe heat flow can give accurate results. But heat flow from BSR has considerably, they should be lower, higher uncertainties, no, it's correct, higher uncertainties than the probe. The second message is that to derive an accurate heat flow from BSR, many critical parameters need to be well constrained. So we discussed them before. It's important to take care of all these parameters when you try to do this BSR-derived heat flow. The last one is that both are very complementary. So they are measured in different depths, and they give information on different lateral extent. And they can help in certain cases to interpret geological and fluid flow processes. So thank you. I just want to inform that that if you have any questions later than this 24 heat flow day, global heat flow day, that you can always contact us at the Marine Heat Flow Working Group. So this is a working group at the International Heat Flow Commission. There is Florian, me, Rob Harris, Raquel, Negrete, who are in the commission, but other people can also be contacted. So don't hesitate to contact us for any questions that you have.